Second lecture in chapter 15 is going to cover solution composition molarity, and we're going to get into some more calculations with molarity. Molarity, and we're going to use a capital M, is going to denote the moles of solute per volume of solution in liters. So here's our formula. Molarity equals moles of solute over liters of solution. For example, to make a 3 molar solution of hydrochloric acid, 6 moles of hydrochloric acid into 2 liters of solution. 6 divided by 2 is 3. This works really similar to the way that the density formula works. So density is mass over volume. Density was, of course, how many grams per liter or milliliter that a substance would weigh. And if we look at this, we're talking about the number of moles per liter or milliliter of solution. Molarity is defining it as liters. So molarity and density have some similarities. The exercises. You have a 1 mole of sugar in 125 milliliters of solution. Calculate the concentration in units of molarity. So the way we're going to have to look at this is to remember that molarity, big M, equals number of moles, little m, divided by liters of solution. In this case, we're given 1 mole of sugar in a total of 125 milliliters of solution. That has to be changed to liters first. So to change milliliters to liters, we're going to go back 3 times. So 0.125 liters. And I know the question is going to be asked, well, is it okay if we leave it in milliliters? And no, it's not. If it's going to be units of molarity, it is moles per liter. So we're going to take 1 and divide it by 0.125, and our solution would then have molarity of 8. Or it would be considered an 8 molar solution. Go ahead and check our answer. Do another exercise. Okay, it says a 500 gram sample of potassium phosphate is dissolved in enough water to make 1.5 liters of solution. What is the molarity of the solution? Okay, let's first of all remember that molarity equals moles over liters. And we're given a 500 gram sample of potassium phosphate, which the formula is K3PO4, so here naming comes back into play, and is dissolved in enough water to make a total of this many liters, 1.5 of the solution. So in order to calculate the molarity, it's no big deal, but I have to know the number of moles, and what I have is grams. I can go ahead and fill in my liters here, 1.5 liters. We're going to have to come over here and find the molar mass of potassium phosphate. Potassium is going to be 3 times 39.1. Phosphorus is going to be 1 times 30.97. And we have oxygen, which is 4 times 16. We're going to go ahead and do the math real quick. 117.6 here. This is going to be 30.97. And 4 times 16 is 64. Go ahead and add all that together and get a total of 212.57 grams per mole is the molar mass. So we're going to take the 500 grams, we're going to multiply it by 1 mole over 212.57 grams so that our grams cancel. 500 divided by 212.57 is going to be 2.35 moles. That's what we're going to put up here, 2.35. We're going to take that 2.35 and divide it by 1.5 and get a molarity of 1.57 molar solution. So the molarity of that solution is 1.57. Let's look at another exercise. You have a 10 molar solution of sugar. What volume of this solution do you need to have 2 moles of sugar? And here, again, it's just simple algebra 1 manipulation, remembering that molarity is moles over liters. We know the molarity, so we have 10.0 molar equals 2 moles over X liters. Just like with the density formula, there's some confusion. Remember that if there's nothing here that's over 1, another way to look at this is that's like saying 10 moles over 1 liter equals 2 moles over X liters, and cross multiply like this and solve for X. Or if you can manipulate it algebraically, if I happen to think through that, again, you cross multiply and solve for X. So either way we do it, we have 10 times X equals 2 times 1 in this case. So we take 2 divided by 10. X equals 0.2 liters of solution, and that's your answer for that problem. Another example, consider separate solutions of sodium hydroxide and potassium chloride made by dissolving 100 grams of each solute into a 250 milliliter solution. Calculate the concentration of each solution in units of molarity. You notice that for each one, you're given the mass instead of the moles. So what you have to do is convert 100 grams of sodium hydroxide into moles and divide it by 0.25 liters, because we can change that easily like this, and do the same thing for potassium chloride. If you want to pause the screen right now and go ahead and work that out, I'm going to go ahead and show you the way the book worked it out just to save time on the video. So if you need to pause it now, try to work it out and check your answer. Otherwise, we're going to go ahead and go on. The answer is a 10 molar sodium hydroxide solution. And it shows here that the potassium chloride is a 5.37 molar solution. It shows you how to make sure that you have the right calculations, changing grams to moles and then dividing through by your number of liters. Look at another one. You have two hydrochloric acid solutions. One is A, one is B. A has a greater concentration than B. Which of the following statements are true? If you have equal volumes of both solutions, solution B must contain more moles of hydrochloric acid. If you have equal moles of hydrochloric acid in both solutions, solution B must have a greater volume. To obtain equal concentrations of both solutions, you must add a certain amount of water to solution B, or adding more moles of hydrochloric acid to both solutions will make them less concentrated. Correct answer is B. If you have equal moles of HCl in both solutions, solution B must have a greater volume. And that should make a lot of sense, because when you look at it and it says that A has a greater concentration than B, if you had equal amounts of them, A would have more moles of HCl in the same amount of solution. So if we wanted to equal those out, our B would end up having a greater volume in order to balance that out. All right, let's look at concentration of ions. For a 0.25 molar CaCl2 solution, we know that CaCl2 is an ionic compound, and that when you put it in a solution, it's going to dissociate into its ions. And for every 1 calcium chloride unit, I'm going to have 1 calcium ion and 2 chloride ions break up from that when it's in solution. That means that there's 1 times 0.25, so 0.25 molar of the calcium chloride, and we have twice that of the concentration-wise of the chloride ion, because for every 1 calcium, there are 2 chloride ions. It's similar to what we covered when we talked about moles of substances as well. Which of the following solutions contains the greatest number of ions? 400 milliliters of a 0.1 molar sodium chloride solution, 300 milliliters of a 0.1 molar calcium chloride solution, 200 milliliters of a 0.1 molar iron 3 chloride solution, and 800 milliliters of a 0.1 molar sucrose solution. Now we know that it's not going to be the sucrose, because sucrose is a compound that's covalently bonded, so it doesn't form ions. It has molecules instead. So if we take a look at these, total ion-wise, if I had 0.1 molar solution of sodium chloride, let's see how many moles I have in that solution. So I'm going to take 0.4 times 0.1. So in this solution, I'm going to have 0.04 moles of sodium chloride ions. In the 300 milliliter, I have 0.1 molar, and I have X over 0.3 liters. So 0.1 times 0.3 is going to be 0.03 moles. So we have fewer moles here. If I have 0.1 molar, whoops, change that. If I have 0.1 molar solution of iron 3 chloride, and I have a total of 0.2 liters of that. I'm going to take 0.1 times 0.2 and come up with 0.02 moles of solution. So total number of ions, we have 2 separate ions here, we have 3 separate ions here, and we have 4 separate ions here. So if I take 2 times 4, we end up with 0.08 moles of ions. If I take 3 times 3, I end up with 0.09 moles of ions total. And if I have 0.02 molar here and I have 4, I have that times 4, so it's 0.08 moles of ions. And when I say, the reason I multiplied this by 2 is there are 2 ions. You're going to have 1 sodium for every 1 chloride. This one you're going to have 1 calcium, and for every 1 calcium you're going to have 2 chlorides, so it's 3 total for every 1. Iron is going to have the iron plus 3, and you're going to have 3 chlorine for every 1, so a total of 4 ions that we're going to separate out for each molecule. That's why I multiplied them by 2, by 3, and by 4. So the one that's going to have the greatest number of ions, like this already starts to show, is going to be B, which is the 0.09 moles of ions. The last thing we're going to cover quickly in this section is standard solutions. A solution whose concentration is accurately known is known as a standard solution. To make a standard solution, we weigh out a sample of the solute, you transfer it to a volumetric flask, and you add enough solvent to fill up to the mark on the flask. So if I say I have 500 milliliters of a 3 molar hydrochloric acid solution, in that 500 milliliters, it includes the amount of hydrochloric acid that it takes to make it that particular molarity. So the weight solute does not, it's figured in when we do the total volume that we're going to fill it up to. And this is the way I'd mix a solution up in the lab. I put a weight amount of the substance into the flask, add a little bit of water, dissolve it, gently swirl it, maybe put a stopper in it to swirl it, and then go ahead and fill it up to the line that's going to take it up to the amount or the volume that is that I'm looking for, that was particularly marked for, and then I have that particular solution prepared, usually at 500 milliliters solution, 500 milliliters of that solution, depending on the size of what this volumetric flask is. But it's already marked, so I don't have to get a graduated cylinder and add so many times of 100 milliliters or whatever it is. As long as I put my solute in there and I fill it up to that line with water, once that's dissolved and fill it to that line, I have 500 milliliters of that solution. I can calculate the molarity, and then I can use it as a standard solution in the lab. That's going to be one of the things that you do when we get ready to do titrations, is you're going to mix up your standard solutions, and then I'll give you unknown solutions to work with.